Okay, good morning, everyone. We'll start this group lecture. So I'll first talk about some basic physics of graphene. So these are some slides that I gave for colloquium some years ago. So I go through a few slides as an introduction, then we'll get into some of the mathematics. So graphene is a single atomic layer of atom. They're all carbon atoms. It is the thinnest material in the world, only 1 atom thick, and it has the simplest structure of all materials, I think, because just 1 layer of atoms in honeycomb lattice, very simple. I think, to my knowledge, I think this is the simplest structure of materials. Okay. And it has a very high symmetry. It has time reversal symmetry, and it has reversion symmetry, inversion symmetry, and it has the rotational, threefold rotational symmetry. Actually, in this case, it's sixfold rotational symmetry. And in 2011, the Nobel Prize was given for graphene. This is the number of publications related to graphene. In different years, you can already see that the production of isolated graphene will happen in 2004. Yeah, but even before that, you already have some work related to graphene. They're mainly theoretical works. Actually, the first calculation on the band structure of graphene in the 60s. Yeah, a long time ago. So there are already quite some theoretical studies on graphene, even before the experimental work. So you can see that starting from 2004 and 2005, then there's a sharp rise of publication. And I started my PhD in 2006 at Columbia. So at that time, graphene was a very hot topic. I mean, Philip Kim was in graphene, and it was in the research of graphene at Columbia at that time, and then Tony Hines. So I happened to be to start my PhD at the time that graphene rose. So very naturally, my thesis was in graphene, and I spent basically my whole PhD just on graphene. Okay. So I'll skip this. So let's look at graphene. So graphene, they are formed by carbon atoms. So in carbon atoms, there are 6 electrons. 2 of them are in the 1s state. 4 of them are in the outer part. Okay, actually, 2 of them are in 1s state, 2 of them are in 2s state, and 2 of them are in the p state. So they will form the sp2 orbit. So we don't need to worry about this 1s electrons. They're in the inner core. Okay, so what we will concern is these 4 electrons in the outer part. So these 4 electrons, 3 of them will form an sp2 band, and the other one will occupy the pz orbit. Okay, if you look from the top, then you have something like a fan. Okay, with 120 degrees threefold rotational symmetry. So if you have a lot of these carbon atoms formed together, then this sp2 bond will overlap with each other between the atoms, and then they will form the bond. Once they form the bond, then the energy will be lower. So this will make the structure stable. Okay, so this sp2 bond makes graphene very strong. Okay, carbon-carbon bonds are strong bonds, and you can already feel this in the phonon band structure. You can, when you measure the Raman, the phonon band has a high frequency in about 190 something milli-eV. So that means the phonon energy is high. That means the bond is strong. Okay. But this pz electrons are not bonded. So the pz electron, okay, this sp2 electron, they're bonded. They give rise to the structural stability and mechanical strength. But these pz bonds are not bonded. So the pz electron can hop from one side to another and they become mobile. Okay. And this hopping pz electrons will give the electrical conduction for graphene. So graphene have both a strong mechanical strength and also conduction. And this is a very interesting feature because usually if a material has a very strong mechanical strength, it is not conducting. For example, for insulator, for diamond, for some other for example, quartz, it's very strong. There's a strong bond, but the electron, because they're strongly bonded, they cannot hop from one side to another. So usually, when you have strong mechanical strength, you don't have the electrical conduction because the electrons are bonded. But for example, if you have a good electrical conduction, let's say in metal, the electrons are free to move. Because they're so free, so the bond is not very strong. Then they're not very strong. Like a lot of metal, they're kind of flexible, and not as strong as quartz or diamond. So you usually don't have both the mechanical strength and the electrical conduction. But graphene has both. Because it has two sets of electrons, the sp2 electron gives rise to the structural stability. Make it very strong. Actually, graphene is the strongest material in the world, even stronger than diamond. Diamond has sp3 electrons. So the bond is, I think, is slightly weaker than the sp2 bond. So graphene is actually the strongest material if you consider the strength in the atomic scale. But at the same time, graphene also has very good electrical conduction. So this is kind of a magical combination of material property. You have good, very good mechanical strength and also very good conduction. Okay. So the theoretical calculation of the band structure of graphene, actually not on the 60s, my mistake, not on the 60s. It's actually in the 40s. The first paper was in 1947. This paper by Wallace. I think the citation of this paper just stood up after 2005, because people study graphene, they go back to check the theoretical calculation. So not on the 60s, in the 40s, even earlier than the 60s. Okay, so if you calculate the band structure of this pz electron, the hopping, you will find that you form a band structure like this. This is the xy plane is the momentum. The z plane here is the electron. So the band structure has this cone-like structure at the Fermi level. Okay, so later we'll calculate this band structure. Okay, if you zoom in, so this is what we call the Dirac cone. It has a cone-like structure, and this has a linear dispersion. The slope of this linear dispersion gives you the Fermi velocity of the electrons, which is about 300th of the speed of light. So the speed of light is 3 times 10 to the 8 meter per second. So it is about, the Fermi velocity here is about 10 to the 6 meter per second. So this particular degeneracy here, this is what we call the Dirac point. This degeneracy is protected by symmetry. So it's something robust, protected by symmetry. In order to open a gap, you need to break the symmetry. For example, break the inversion symmetry. Like in boron nitride, you break the inversion symmetry. That's why you open the gap. In MOS2, you also break the inversion symmetry, so you open the gap. Okay, if you like calculate the band structure, you'll find an effective Hamiltonian in this form. So this is the K vector. You count it from the K or K prime points. And there's a very simple form, H bar Fermi velocity times sigma dot K. Okay, sigma is the Pauli matrices. So later we're going to calculate this Hamiltonian. Okay. So here the basis is the A and B sublattices. So in a unit cell in graphene, there are 2 bases, A and B. Okay. So So here, the basis of the Hamiltonian is the A and B sublattices. And you can make a comparison with the other kind of electrons. For example, for a conventional semiconductor with a quadratic band, then they can be described by the Schrodinger equation. Is P squared over 2 effective mass. This is the conventional electron system. If you calculate the ultra relativistic Dirac particle, okay, then that means you assume the speed is very, very high, very close to the speed of light. Then the Dirac equation will give you this Hamiltonian sigma dot p. And then in graphene, you can see that the Hamiltonian is Fermi velocity sigma dot p. It's very, I mean, essentially it has the same form with the Dirac equation, except that for the Dirac equation, this sigma would give you this spin, okay? And here the sigma, it corresponds to the A and B components. So the A and B component of the sublattices, they behave like the spin, and we call them the pseudo spin. Pseudo means it's fake. It's fake, not really spin, but they behave mathematically like the spin. So and you can see the sigma dot p means the A and B component, they are coupled with the momentum. They're coupled with the momentum. So graphene has a very high electron mobility. So for silicon, the mobility is about 1,000 centimeters square per volt times second. So this is a typical unit for mobility. So for silicon, it's 1,000. Okay, but for graphene, it's very high. It's 500,000, and this is the value some years ago. I think now people can improve it to million or even higher. I think it's in the order of million now. Okay, so this was the PowerPoint I made some years ago. Okay, so now the device quality, I think, is already improved. And there are a few reasons why graphene has this high mobility. The first reason is, let's see. Okay, the first reason is because it has zero mass. When there's no mass, you can expect an easy acceleration. Okay, it's much easier to accelerate an electron than accelerate an atom, because electrons are light. And here you have zero mass, so you can expect easy acceleration. This is some intuitive picture, okay? And another interesting thing is the chirality property. Because in order for the electron to get scattered you actually need to change something called the chirality. And this chirality is something robust. So you make it insensitive to potential barriers. And another very interesting feature is that carbon atoms are very light. They're not heavy, okay? And the bonds are very strong in this case. You have a strong bond and the light atom. Then the result is that you have high optical phonon energy. You can imagine a two mass problem. Like you have two mass connected by the spring, okay? If the spring is strong and the mass is light, then the frequency will be very high. After you quantize it, then the quanta of the energy is strong. So graphene has an optical phonon with the energy near 200 millieV. Okay. So if you consider the thermal energy at room temperature is about 26 millieV. So this is much higher. So that means at room temperature, there's essentially no optical phonons in graphene, no optical phonon. So that means the population of the phonon is small. So there will be a lack of electron phonon scattering. So when the electrons travel in graphene, it's difficult for it to scatter with the phonon because the phonon has high energy quanta. Okay, you need quite some energy to excite a phonon. Okay, so when you combine this, you can see that the electrons are light, zero mass, easy to accelerate. They're not very sensitive to potential barrier, and they don't really scatter with the phonon that much. So a natural consequence is that the electrons just travel like it is nothing. There's nothing there. So that's why the mobility is very high. Okay, you get the idea? So graphene has a lot of like this combination of material virtues, which make it special. Okay, so so that's the introduction on the materials. So then we go to the mathematics. Okay, we go to the mathematics. So the first thing we'll consider is this sp2 bond. Okay, sp2 bond. So let's look at this atom. Okay, so so you have a carbon atom in the middle, and then you have 2 electrons. Okay. Yeah. Why this? Do it again. Okay. Now it works. Okay, you have a carbon atom in the middle, 2 electrons, and then you have another 4 electrons. I mean, this is a very simple cartoon. I think I can make it. Make it look better. Okay, another one. Okay, so you have a carbon atom in the middle, the nucleus, and then you have an electron here. You have an electron here. Okay. So this is a very simple cartoon. So if you draw it out, you have 2 electrons in the 1s state. 1s state. One is spin up, the other is spin down. Okay. The other one is the 2s state. Also, one is spin up, the other is spin down. Then here you have 6 different states for the 2p. The 2p. And you have 2 electrons, and usually you have 1 electron on 2 of the p states, and they're both spin up. So this is the ground state of an isolated carbon atom. Okay, the ground state. So now, but this ground state is not very good for the carbon atoms to form a chemical bond. In order to form the chemical bond, we'll consider a slightly different combination. Okay. So we'll consider this. We're going to take away this. We're going to take away this electron for the 1s state, and then put it here. Okay. So this is an excited state. So the excitation S to P causes some energy. But so this is not the lowest energy state for isolated carbon. But once you have some carbon atom form a chemical bond, then the energy will be lower. And it turned out that this state has a lower energy after the bonds are formed. But it will be compensated when the bonds are formed in graphene. So we're going to consider this this state. Okay, so later we are going to consider a combination between this 1s and 2p states. So they will hybridize. They will hybridize. They will hybridize to form a 3sp2 states. And then together you have a PZ state. Okay. So what do you mean hybridization? What do you mean sp2 hybridization? It's basically a linear combination of this S and P states. So the S state has a wave function like this. It's a sphere. Okay, spherically symmetric, and plus and minus. So this is the px state. So plus and minus means the sign of the wave function. Okay. So yeah. Let me just copy it. So this is the py state. So we're looking on the top view. Okay, we're looking from the top view. So the plus and minus are signs of the wave function. Anyway, if you're not familiar with this, just go back to review the wave function of the hydrogen atom. Okay, once they hybridize, so let's draw the X and Y. So once they hybridize, they can form a 3 states. So let's draw the wave vector first. Let's draw the wave vector first. Okay, so this will be, we'll just say py px minus py, and then this will be negative px minus 1/2 py. You just use the algebra of a vector. So this 3 vector will have a coordinate like that, and you just convert it into the momentum space. Okay, consider 3 vector. So we're going to have 3 hybridized wave function. So this is the wave function with this combination. First, you just consider the S state plus the py state. Okay. So this is one hybridization because you want this component. So you have the S combined with the py state, and of course you need to add the normalization factor. So the normalization factor is just alpha squared plus 1 square root. So it will be 1 plus alpha square root. So alpha is a parameter which we'll determine later. Okay. Then you have another state, this state. So this state we just draw it like that. Okay. And then you have the same normalization factor. And then here you have the S state, and you have plus need some space. And then you just use this coordinate. You just use this coordinate, okay? You use 3/2. And then you will be the 3/2 will be the px state and 1 minus 2 py state. Okay. Get some space. Okay. Then you have another one. We just copy and paste. And then you just change this. Change this. Change this. Okay. So all you need is change the direction. And then this is a negative sign. So you just change the negative. Yeah, okay. So these are the three states. They are linear combination of the S px state and the py state. So you have this three state, make a linear combination, and then you form another three states. Okay. These three states need to be orthogonal to each other because they're the new eigenstate. So they will be orthogonal. So you can get this state and this state. They're equal to 0. Okay. Then you just make the product. Okay. Make the product. Then you it's very easy because this will give you alpha and this will give you negative 1/2 and this give you 0. You just make the inner product. So you have alpha square minus 1/2. So it need to be 0. Okay. It need to be 0. Okay. It need to be 0. So alpha just equal to 1/2 squared. Okay. And then 1/alpha square square root means 1/2 square root. And then this is 3/2 square root. This 1/2. Okay, so you get the value of the alpha. So for this this is not the spin. Okay, the arrow is not the spin. It's just the direction of the band. Okay, the direction of the band. So you have 3/2 and then 1/a state plus the py state. Okay. So let's look at the wave function. X y. So for the wave function is something like this. It's like a dumbbell. Okay. I want to draw it better, but okay, you get the idea, like a dumbbell. And this is plus, this is minus. Okay. Let's draw it better. Plus. This is minus. Okay. And then the air state. The air state. the S state is just a sphere. Okay, it's a sphere. Maybe just draw it like this. Okay, yeah. Okay, and it's a plus, plus. Yeah, and it's plus. It's plus. I mean, the plus signs are not very clear. But anyway, you get the idea. Okay. So after you sum together, what will you get? After you sum together, you sum them together. You sum them together, so you get something like okay, you just sum them. This is plus, this is plus, this is plus, this is minus, this is plus. So on one side they will get enhanced, on the other side they will cancel. Okay, so you get something like a bigger part, and then the other side gets small. Is okay. So you get something like this. Maybe I should make it bigger. Make it bigger. Okay, so you basically get a bigger dumbbell on one side and a small one. Okay, something like that. I think maybe it's even longer than that. Maybe it's somewhat longer. I don't know. Anyway, you get the idea. Okay, so you have the same thing for the other two. Okay, so eventually the bond will look like this. You have one, and then a small, and then the other one. Let me use a different color then. Okay, the other one. Can I copy this? Okay, something like that. Yeah, something like this. Okay, and paste. Something like that. I hope you get the idea. Okay, then you have the small part here, and the small part here, negative. Okay, so this is what the bond look like. So this is the sp p2 orbitals. Okay, so this is the sp2 bond. Then you have the pz bond. The pz bond is in the perpendicular direction. So let's go back to this slide. Okay, so what we have already calculated this orange bond from the top. is the sp3 bond, 3 of them, and they form a 120-degree angle and have 3-fold rotational symmetry. And then you have another pz state. It is also a dumbbell, but the dumbbell is on the z direction. Okay, so these are not involved in this sp3. Okay, so once you have a network of carbon atom, this sp2 bond, once they touch each other, they will form a bond and the energy will be lower. Okay, will be lower. So you can see that at the beginning, this is the ground state of the carbon atom. In order to form the sp2 bond, you need to excite one of the two s state into the 2p state. So this will cause some energy. Okay, but once they form the bond, okay, once they form the bond, the energy will be lower. Okay, and that energy will compensate the energy of this excitation. Actually, will compensate even more to make that a lower energy state. Okay, so that means in graphene, although each carbon atom is in a higher energy state than an individual carbon atom, but once they form a bond, the chemical bond will make the energy lower, and that will make the whole network of sp2 bond has a lower energy than isolated carbon atom. Okay, so that justifies why you can excite a 1s state to the p state and the structure is still stable. Is it okay? Okay. You have something similar for diamond. Okay, for diamond, all you need to do is you add the pz state, and then you do something similar, and then you have a sp3 bonding in this 3 direction. Okay, and then you form a network, and that form a diamond lattice. Is okay? And of course, the coefficient, everything need to change, but using the orthogonality relationship, you can get something similar for diamond. Okay. Okay, so that is the physics for this sp3 hybridized orbital. You have any questions before we move on? Is it clear? Okay. Okay, that's good. Okay, so next we'll consider the pz electron. The pz electron will hope. Okay, so this pz electron is just once you solve this problem of the sp2 bond, then the pz electron can be treated isolatedly. You don't need to worry about the sp2 electron anymore. You just treat it as a background, and this electron, pz electron, will just hope. So from now on, we don't say pz electron anymore. We just say this electron. Okay, so there's one available electron in each atom, and it can hope from one side to another. And we're going to get the energy band structure for this particular pz electron. Okay, is it okay? So now let's consider graphene lattice. So the graphene lattice. Okay, so we talk about graphene. So the unit cell of graphene. So let's first draw the atoms. So let's first draw the atoms. Okay, my drawing is not very good, but you get the idea that this is a honeycomb lattice. It look distorted. Okay, it look distorted, but you get the idea. Okay, so the unit cell has a vector like this. Something like that. Okay, you get the idea. Okay. So this is the A atom, the A lattice, and the B lattice. Okay. So we're going to take this length as a A. So this is the bond length between two carbon atoms. Then this vector we're going to call it R1. We're going to call it R2. So this is A. So this area here, this is the unit cell. This is the unit cell. And from the unit cell, we can get the basic vector. The basic vector for graphene R1. So what is the coordinate for R1? Then you just solve this problem. So what is this length in the x-axis? So this is 3/2A. Because this is A, this is 1/2 of A, so it's 3/2A. Okay. 3/2AX. And what is the length of this one? Then you just solve this problem. Okay, it's a very simple problem. Then you find it's 3/2AY. Okay. Then the other one is very simple. The other one is you just change the sign. So this will be 2, then it will be minus. So that's it. These are the two basic vectors. Okay, so we're going to consider the basis. So that means for each atom, you have going to have the PZ state. Okay, that PZ state has a particular wave function. Okay, and we just use it RA to represent the PZ state at that particular atom. So this whole set of wave function form the basis. Form a basis of the electron. Okay. Of the Hamiltonian of graphene. Of course, generally, they are a set of one-yen function. But here, you just simply use the PZ orbital. Okay. But generally, they're the one-yen function. Okay. And of course, here you're not considering just one electron. You're going to have more electron. So you're going to feel it. But anyway, we take one electron first. The electrons. But for now, we just consider. Okay. So the RA state and the RB state. So we set the on-site energy to be 0. So H is the Hamiltonian of the graphene. You set the on-site energy to be 0. we set the on-site energy to be 0. It's just a setting, okay? I mean, you need to set an energy 0 point. You just set it there, okay? Then for RA and RB, this overlap, we set it to be T, or RB over RA. So if RA, RB are nearest neighbors, neighbors, and then you set them to be 0, to be 0. If they're not 0 nearest neighbors. So in this simple calculation, we only consider the hopping between the nearest neighbors. But in a more general calculation, you can consider the next nearest neighbor hopping. That will modify your band structure a little bit. But let's consider the simple case. Because the further away they are, the hopping will become weaker and weaker. So let's just consider nearest neighbor hopping. So what does the Hamiltonian look like? The Hamiltonian of graphene will be something like this. You have the hopping parameter, and then you have the RA, RB that are nearest neighbor, and then you have a RA, RB plus RB, RA. Okay, and then here this different one-yen electrons, different one-yen states, they are 0. They're orthogonal. Okay, so this will be the Hamiltonian that we're going to solve to get the band structure of graphene. Is it okay? Do you have any questions before we move on? Okay, if no, then now let's consider an alternative basis. The Fourier transform of the one-yen basis. So we're going to define this. We're going to define a K equal to this RA it's just a Fourier transform. And then BK, I just copy this thing. And then you just change everything into B. Okay, so this is just a Fourier transform. So each of this is the pz orbital for each carbon atom. You make a linear combination like this, then you get the Fourier transform. So this is the A sublattice state. This is the B sublattice state, and they are a function of K. K is the wave vector. Is it okay? So this is a very common strategy for the time binding model. So we're okay. So let's get the Hamiltonian in this basis. Let's get the Hamiltonian in this basis. So from the relationship, RA linear product with RB equal to 0, and then RA prime. This is a delta function of A and A prime. So A and A prime are two different two A sites. They can be the same site or different sites. If they're the same site, is 1. If they're different sites, is 0. Okay. Then let's get the AK state. Okay. So let's get this part. Copy. This will, and then we're going to get the RA prime in the product. So so this will get the RA prime in the product. Okay. So what will it look like? Let me see. This will be delta A prime A. Okay. Then that means you by the way, this n is the number of atoms. Then you have the delta function here. You can collapse this summation. Then you will only have one term left. That is the A prime. Okay. So similarly, you have the same thing for the B. You have the same thing for the B. You just change everything into B. B. Okay, you just change everything. Is RB prime, BK. This is B, and this is B prime. Okay, so you get another one for the B. Okay, now, so let's get the matrix elements of Hamiltonian in this AK and BK basis. Okay, so let's get AK and H and AK. So let me see. So what is H? We already have H here. So this is H. This copy this H. Okay. You copy this H. And then you just have the A. Okay, you just have the AK on this side, AK on this side, AK on this side. Okay, so these are just some simple algebra. Okay. Okay, then we can get the calculation. What is this? This is 0. Because this AK are all in terms of the Ra atom, and this is a Rb atom. So the inner product will be 0. Okay, you can see AK, they're all they're all in Ra atom. Okay, when you have an inner product with the Rb atom, you're going to get 0. Okay. And let me see. And the same for here. This is 0. Rb and AK is 0. So you just get 0. Okay, you just get 0. So similarly, BK this is also 0. Okay, it's also 0. That means the diagonal elements of the Hamiltonian are all 0. Okay, so let's get the off diagonal elements. AK and BK. Okay, so for this one, then we just do the same thing. Okay, we're going to just do the same thing. Copy. Then of course we're going to change this. This won't be 0. So we all need to change this into the BK. Into the BK. Okay. Then let's see. This one is still 0. So this term is 0. Okay. So all we need to do is to consider one of these parts. Okay. So all we need is this, just this one part. Okay. Let me see. So what is this? What is this? BKRB, we already get the answer. We already calculate this. BKRB prime is this thing. Okay. So we just copy this. Okay, we get this part. This will be this. Okay. And what about this? Yeah. What about this? This RAAK. RAAK is this one. RAK is this one, but they are complex conjugate with each other. So you get this copy. And this is A. This is the A, not the A prime. Okay. And this one, you need to add the complex conjugate. Let me use a red color. Complex conjugate. Because this AK is on the other side. Okay. So, and still you have equal copy. Okay, you get the idea. Okay, so let's continue. Let's continue. So we just combine them together. Then this 2n will become just 1 over n. Then you can move it out. T over n. T over n. And then this one, you just combine them together. You just combine them together. It will be, just write it again. Will be E I K dot RB minus RA and their nearest neighbor. Okay. Okay, so how many nearest neighbor? There are three of them. There are three of them. So let's go back and consider. Let's say you have the A atom. You have the B atom. And then you have another A atom here, A atom here. So you consider the lattice is something like this, right? Okay, you consider the lattice. Okay, so let me call this a A1. This is A2. This is A3. So there are totally three of them, right? So you just consider. Let me make this a bit smaller. Put it here. Okay. So then you only need to sum over all the RB, and for each RB, you are going to have RA1 plus RA2. Okay. And plus, need one more line, plus E. Let me make it slightly smaller. RA3. Okay, so make it smaller then. Okay, so you just sum over them. Okay. Okay, so let's get each one of them. So after you get this RB will just become N because all of them are identical. Okay, so all you need to do is this will just become just N. This whole thing will just become an N. So this N and this N will cancel each other. Okay, so you have Tn times N. Okay, so let's get this thing. What is this? So RB minus RA is just this vector. Basically, just this vector. What is this vector? This vector is this is just A. This is just AX. Okay, so this will be dot AX. Okay.
What's the sum over RB N and not N over 2?
Let me see. Okay. N is not the number of atom. N is the number of unit cell. Yeah. Because we define it here.
Yeah.
Huh? N is the not the atom, number of unit cell. N is the number of unit cell. Oh, Okay, so the next one. So this RB minus A2. This will be this thing. RB will be this thing. Will be this thing. So this what's the this is the value is let me see. This will be this will be, of course, you this value is 1 over 2a minus 3 over 2a y. I mean, anyway, you can get it easily. Okay. Then another one is let me get this. The other one is this. This will be the same, but will be plus. Okay, I mean, I don't bother to get this coordinate. It's straightforward. Okay, you know the angle. Okay, so let's not bother on this TD algebra. Okay, so this one will be negative 1ax minus 2a. Okay, this is another one. Let me get it closer. And then a third term will be okay. So you get all of these terms, then you just do some algebra to simplify them. So this n will cancel. You get a t. Okay. So this one is just this one will give you a kx. So it will give you a kx. And the other one, let me see, how can we simplify it? So this first term is the same. So you can just get 1 over negative IA over 2 and also kx. Then you can combine negative 1 over 2, 3 a ky. And then here you have a ky. Okay. Yeah. So let me copy. So this is just a cosine function. Cosine function times 2. So you just oh yeah, I missed the I. Yeah, I. Okay, get the I. So just times twice of the cosine function. AKY. Okay, so yeah, so that's it. That's it. And then this is the matrix element for this thing. Okay, for this thing. Then we get the matrix element for the other one. For this one, you have the BK, AK. So it's straightforward because this is just the complex conjugate. It's just the complex conjugate. And then you just copy this whole thing. And just you just add the complex conjugate everywhere. Plus, yeah. This will be plus. Yeah, and that's it. Complex conjugate. Okay, we're going to define this thing. Let's make it alpha. Okay, so just set it as alpha as a function of k. So this will be alpha complex conjugate. Okay, so the Hamiltonian is like this. In the basis of AK and BK, this whole set, the Hamiltonian is HT, and then will be alpha K and alpha dot K. Okay, and alpha is this thing. Copy, just write it again then. Okay. Write it better. Okay. Okay, so let's solve this Hamiltonian. It's straightforward to solve it. So the eigenvalues of H are the energy, just this times this square root. That's it. So okay, you solve it, then you get this. So basically is T absolute value. That's it. Okay, so let's get it. Let's calculate it. So E equal to E will be a function of K. Then we get this thing. Copy. Let me shrink it a little bit. Wait. Put it here. Let me just shrink it together. And then wait, is something like this. Shrink it. Then copy this. And then we just change them into complex conjugate. So so this will be minus, this will be plus, and then square root. And give a T here. Okay, so anyway, you just expand it and you get the result like this. By the way, plus minus. Okay, you get plus minus. Yeah, the plus minus should be at the very beginning, because after you open after you open it, you get the square root. Like so it's actually straightforward. Expanded. You have these two things come together, you give a 1. This thing and this thing come together. This one will cancel. So with this will give you a 4 cosine. Cosine 3/2 AKY square. And this one and this one come together, will give you this. And then you sum over with this and this, and you find that they're two complex conjugate together. And you give you this will give you another cosine function. KY KX. Anyway, this one and this one together will give you one cosine function with a factor of 2. Then you have the original cosine function. KY, okay, give you this. So, okay, so you're going to have n electrons, and it will be a half filled band. So, if there is only one electron per site, then the band will be half filled. And the Fermi level is at E = 0. Okay, so let's consider the energy near 0. Let's consider. By the way, you can already plot this thing out. Okay, this is a function. You can use Mathematica or MATLAB to plot it out. After you plot this whole thing out, you get this. You get this thing. Okay, this is the plot of this function. You can try to plot it by yourself. Then you can experience and have a feeling what this thing look like.
Sin kx, you have got square root of 3/2.
Yeah. Good observation. Okay, there's a mistake here. Yeah. So it's just a 3 here. Okay. Thanks for the correction. Actually, it was right on my note. Somehow I make a mistake on here. Okay, so this is the plot. Okay, so when you have one electron per site, you're going to fill the lower band, the lower part of the band. So we're interested in the energy in the state near the Fermi level, because the state near the Fermi level determines a lot of the material properties. So we're going to do a Taylor expansion near this band, and we're going to get the Dirac cone later. So we're going to do the Taylor expansion. Okay. So let's first get where the Fermi level is. Like where is this Dirac point? Where is it? So we're going to solve this. We're going to solve this thing. So where is the Dirac point? So you're going to basically solve this equation. Solve it. So at which K will with this. So that is where the Fermi point will be. And it's very simple. You just basically solve this thing, copy. You solve it for 0. Okay. And let me see how we're going to solve it. You can actually already see that. Okay, so let's get the first Brillouin zone. The first Brillouin zone. Something like that. I'm not a very good hexagon. Can I draw it better? Something like that. I'm not very good either. Okay. You have the K and K prime points. This is because we set the unit cell like this. We set the unit cell like this. Because we set the unit cell like this. Okay. We set the unit cell like this. So this is in real space. And this is in K space. Usually for the reciprocal lattice, it will rotate for 90 degrees. So you have a hexagon like this, and then the Brillouin zone will be like this. Okay. That is our convention, because at the very beginning, when we set the lattice, we already make the orientation like this. Okay. So the Brillouin zone will be like that. Okay. And once you plot it out, you'll find that the Fermi point is at the corner of the Brillouin zone. So that means the kx is 0. So the kx is 0. So you can already set the kx to be 0. So once the kx is 0, so this will be 1. This will be 1. So we all we need to do is to get the this one equal to 1 at kx equal to 0. So yeah, all you need to do is solve this quadratic equation. AKY, this thing. This thing. Square, and then you have 4 cosine AKY. You can take away the 4. Okay. And then this will be 1/4. Okay. So you get a quadratic equation, then you just solve it. Then there is a very simple quadratic equation. So it will be negative, this b is 1, negative b plus 1 over a squared minus 4bc. I think it's like that. So this is 1 is this, 4bc is this is 1/2. So 4bc is just 1, and 2a is 2. So this is just negative 1/2. Okay. Then you have two solutions. So this negative 1/2 for cosine. This is, what's that? This is plus and minus 120 degrees. Okay, so this 2 pi over 3. Okay, so 2 plus or minus give you the same result. Okay, so ky will be plus and minus 4 pi. 3 over 3 with 3 square root. Okay, so you just move this thing to the other side, then you give you the ky. Okay, so the Fermi points are at kx ky equal to 0 and plus. So this is where the Fermi point is. So this is this point. These 2 points. I mean, there's 6 of them, but only 2 of them are equivalent. Okay, so you have this and this. Basically, it's this one and this one. The kx is 0. Okay, so we're going to get the Taylor expansion of the energy near these 2 points, and then you get the cone feature. Okay, so we can expand this alpha near this plus these 2 things. Okay. Okay, so you can name them. You can name them k plus or k. Let me see. K plus k minus. Okay, k plus k minus. Let me simply just anyway, I'll follow this then. Okay, you can actually use a bigger one. Like you can use some people use plus and minus big K. Okay, that plus K is the K value, minus K is the K prime value. Okay, you can name it as plus K or minus K. It's up to you. Okay, it's up to you. Okay, so let's set let's define K plus equal to this K value minus plus and minus K. Here you just set the vector then. Okay, so you have plus and minus K. You use that as an origin and minus it, then you get this plus K. Okay, plus and minus then. Okay, so this plus and minus small k is the K vector counted from the 2K value. Okay, we just define this way. Okay, then you can already set plus and minus the x component because this x component is 0. Okay, so you just get the x component of K, and the plus and minus ky will be ky minus this thing. So after you minus, you flip the sign. Okay. So these are the 2 components. Okay, then let's get the Taylor expansion for alpha. Okay, let's get this alpha. Copy. And from here, you can already know that ky will be k plus and minus y plus and minus 4 pi. Basically, you go to the other side and flip the sign. Okay, so So this E will be IA. KY will be just this. Will be just K. KX. K. I just use KX then, because KX is just the same for both of them. Let's continue just to use KX. KX. Two. Okay, here you have 2A, KY, you get this thing. Copy. You get this thing. Okay. Let's write one more line. Okay, let's write one more line. And so this one you just open it. Let me. Will be K plus and minus Y, and then this one you will get 2/3 3 square root. The A will get cancelled. And then you let me see. You just get 3 high. Yeah, I think that's it. Yeah. Okay. Then we're going to do the Taylor expansion. So the Taylor expansion of this one approximately equal to IAKX. And this one approximately equal to negative IA2KX. Taylor expansion. Okay. Okay, this one we're going to expand it. So for example, a Taylor expansion has you have a function as a x plus delta x. So this equal to x plus you have a d f dx. You calculate it at x and times delta x, right? Okay. So let's say you have a cosine function. Then you will be a cosine x plus derivative of cosine is negative sine function, right? Okay. And then times delta x. Okay, that's the Taylor expansion, right? You have the higher order. So here you're going to expand it here. So okay. So here you're going to expand it here. So this thing will be cosine plus and minus 2, 3 high. It actually doesn't matter plus or minus. Yeah, it give you the same value. So then minus sine plus and minus 2. And then times this delta thing. Maybe move the whole thing. AK plus and minus Y. Okay. Is it okay? Okay, so and this is approximately okay. This is 120 degree, right? So this is negative 1/2. This negative 1/2. And this string will be plus and minus square root 3. To half. Okay, so the whole thing is approximately will be sorry, this tail expense is 1 plus and this is 1 minus. There's a 1 there. Okay, there's a 1 there. Okay, so let's write it again. 1 plus IA kx plus 1 minus IA over 2 kx. And then there's a 2 here. This will times a 2. This 2 minus this will be times this will be negative 1. And then minus sign, this minus sign plus a minus will flip the sign. So this will be minus and plus. And then this 2 combined together will give you 3 over 2. So 3 over 2, a k plus and minus y component. Okay, so that's the result. Okay, then let's expand it. Let's expand it. Okay. I mean, those are tedious algebra, but anyway, we'll do it anyway. Okay, this will give you minus 1, and then and plus IA 2kx, and then this will give you plus and minus 3 over 4. Then you have an a square kx ky. Okay, something like that. Okay, so this last term here can be neglected because we're doing a Taylor expansion. So this one neglect because this is a second order term. Because kx and ky are small, right? But this would be plus and minus k, because we're expanding it near the direct point. So both of these are small things. When you have 2 small things multiplied together, this will be a second order term. So you can neglect it. Okay, so eventually, you will only get how many terms? Okay, so this 1 and this 1 will cancel each other. So eventually, you'll get let me see. This one cancel. This 2 will be I 3 over 2a kx. These 2 combine, and then you have minus plus 3 over 2a k plus y. y. Okay, so then you take the 3/2a out, then you have the I kx minus plus k plus y. Okay. Okay, so we get the result. Okay, for the Hamiltonian. So we know the Hamiltonian is we know Hamiltonian is T 0 alpha. This is the Hamiltonian. Okay, so near plus k, the Hamiltonian, is like, you can use h plus to represent it. So it will be this one, 3/2at. So you use the plus part. The plus part will be I kx plus and minus. So you use the minus one k ky. Here we just simply use a k y then. Okay. Here. Okay, here we just set ky equal to k plus minus y. That means this ky is not the absolute ky. Is the ky counted from plus k. Counted from plus and minus big K. Okay, so you get a familiar form. Okay, so then near minus K, the Hamiltonian is like, then you have the other part. Okay, so you have I kx, it will be plus ky and negative kx plus ky. Still, so here we set it. Okay. Okay, so but this form is probably not the same as the one that you see in the paper. So we're going to do a rotation. So because usually here we're setting a Brillouin zone like this. This is the Brillouin zone that we set. So you have the x and y. So let's make a rotation. Rotate the coordinates 90-degree counterclockwise. Counterclockwise. Then you will have the coordinate like this. Okay, so here the coordinate will be what? Will be the x will become y. The x will become the y. Let me see. counterclockwise. Okay. Sorry, y will become x. The y here will become x. The y component become the x. And then the x component will become negative y. Okay, so if you view this on the on a more familiar orientation, yeah. Then it will be this. Okay, so this is a more familiar form that you have k and minus k. So you just follow this. The Hamiltonian will become copy. So if you follow this, the Hamiltonian is you just follow the convention. So this ky y will become x. So this will become kx, and this will become negative ky. So this is kx. This will become negative ky. Then this whole thing will become let me see. Am I correct? Oh, sorry. Rotate the system. Let me see. Did I make a mistake? Okay. This will be minus kx. Okay. Then similarly, let me see. I'm a little bit confused about the sign now. Okay, this one. Huh? Okay, this one will be ky kx, and then will be minus. Okay. Okay, something like that. Okay. Okay, so if you rotate it 90 degree, the coordinate counterclockwise, you have something like this. So this is a more familiar form, that you see in the literature. You see in the literature. And you can do it the other way. It depends on how you rotate it. Basically, if you rotate it another way, let me see. If you're doing another way, if you rotate it, copy. If you rotate it clockwise, then you'll get the plus and minus 0. The coordinate clockwise will be plus and minus kx. Kx. Okay, anyway, so let me summarize it. Copy. If you rotate it counterclockwise, then you basically get this. Flip the sign. Negative plus. Okay, so I know that the transformation is a bit tedious. Okay, so this is the form that you get. The form that you get. So in particular, you get a form that is just very similar to the direct equation. When you flip the value, you flip the sign of the x, but the sign of the y is the same. Okay, so you have two values. So in one value, you have an equation like the direct equation. Okay, when you flip the value, you flip the sign of the kx. Okay. Okay, so now let's in both cases, in both values, the energy, if you solve this, the energy will be just kx plus ky squared. So it will be 3/2 AT k, absolute value. Or you just simply call it just k. Okay. So the Fermi velocity is Vf equal to this formula. This formula, delta E over dk. Okay. Then it will be 3/2 ATH bar. Okay. So you can see that the Fermi velocity is proportional to the hopping strength. When the hopping string is strong, you get a larger Fermi velocity. And it also depends on the length. The length, the bond length, it also depends on. Okay. So this is basically is determined by the hopping parameter of graphene. Okay. So yeah, more or less that's it. I think we already spent about 2 hours. You're probably already tiring. Okay, so so what is the Fermi velocity in this case? So you can see that from this going to here. So you can see that the H energy is H bar Fermi velocity. Let me see, times k, I think. Yeah, times k. Okay, and then this Hamiltonian, this one is h bar, so you can replace it. You can replace it by this. Okay, so basically you have this thing, copy, and then the h bar. So you can also write it in this form, in Pauli, the Pauli matrix. Let me see. Okay, so the Pauli matrix is sigma x equal to 0, 1, 1, 0, sigma y equal to 0, negative I. Then it will be, let me see, it will be, you have the kx plus and minus kx 1, 1, and plus and plus ky minus this one is better. Let's get this case. Okay, let me get this case. You need to pick the right orientation to go back to the Dirac equation. Let's pick the better orientation. Okay. Okay, let's pick this orientation. Okay, so yeah, my Pauli matrix is gone. Sigma x, sigma y. Okay, so it will be this. Will be minus plus kx, and then plus ky, negative I. Okay, so this is sigma x. This is sigma x. This is sigma y. Then you have minus plus kx. Okay. Yeah. Okay. So you have this k dot sigma, and you need to use let's tau denotes the value. Okay. So you have a tau kx sigma plus ky. So tau denotes the value. Okay. So this is a form of a Dirac equation. Okay, this is a form of the Dirac equation. So of course, when this is plus, then this is just k dot sigma. When it is on another value, then you need to flip the sign. Okay, then you need to flip the sign. So I think in some of the theory paper, you probably see the Hamiltonian of graphene like this. And for MOS2, is basically the same, except that you add the sigma z term. So let me quickly comment on MOS2. So you quickly get the Hamiltonian of MOS2. For MOS2 or BN is just the same thing. But the only difference is that the drawing is not good, sorry. The only difference is that the A and B are different. So you have the A and you have the B. So A and B has different energy. Why? Because for Bn, this is a B, this is an N. So the two lattices are not the same. For MOS2, one is MO, the other is S2. You have the top and bottom S. But when you look from the top, you can view it as one side. And that side is different from the other side. So A and B are not going to have the same energy. But they are still forming a honeycomb lattice from the top. You can just use a honeycomb lattice to do the calculation. Okay. And eventually, the Hamiltonian will be just the same as this one. Copy. Will be just the same as this one, except that you need to add the z term here. All right. Of course, the Fermi velocity will also be different because the hopping will be different. Then all you need to do is to add the energy here. This will be the on-site energy. You can just use what should I use? Just the energy, or you just add the delta here then, plus delta minus delta. Okay, you just open the gap. The delta can be big, can be small. You add the delta here. So if you write this as a function, so if you write it out like this, okay. Then you have another, I should not call it delta because, yeah, you can use delta, but the delta needs to times this to get the energy gap. There's a factor here. Okay, so you add a delta plus delta, then this will be sigma z. Sigma equal to 1 minus 1. Okay. So this will give you a gap. This will give you the dispersion. So when sigma is 0, no gap, then you get a cone. Okay, so this is what you get in graphene. So when sigma is not 0, then you will get something like this. You open the gap. So the gain gap size is twice of this delta. Okay, so you open the gap. So we call this a massless Dirac fermion. Sorry for my handwriting. Fermion, and this is is a massive Dirac fermion. So basically, graphene is a system of massless Dirac fermion, and boron nitride and MOS2, MOSE2, they are massive Dirac fermions. The only difference between them is the on-site energy. Graphene has an on-site energy of 0. Two of them are exactly the same. But boron nitride, MOS2, each of this have different energy. Okay, so this will open the gap. But for MOS2, of course, it's not sp2. It's a bit more complicated. You have different bands due to spin-orbit coupling. But no matter what, the electron need to hop. Okay, once the electron hop from one side to another, then you just follow just the same calculation we did for graphene, and you will get an effective Hamiltonian. With the on-site energy difference, then you'll get the band structure like this. So far we haven't considered any spin-orbit coupling or anything related to spin. You just consider honeycomb lattice with the hopping, then this effective Hamiltonian will behave just like give you the form of a Dirac equation. Okay, with the on-site energy difference, you open the gap. Without it, you have no gap. So that is you can say the simple structure behind the physics of graphene. Okay, do you have any questions? Okay, so you have a lot of interesting properties coming out from this chirality, optical selection rules, those things. We'll talk more about this later. And you also have the Berry curvature. So once you have the Hamiltonian, then you can calculate Berry curvature. You can calculate the state wave function. You can calculate the optical selection rules. You can calculate the Landau levels. All those things, they have the root from this effective Hamiltonian. They have the form of a massless or massive Dirac fermion, the Dirac equation. Okay, you have any questions? Okay, if no, then I'll end the lecture here.